thank you very much for the invitation. It's an honor to be able to come and speak to this group. The picture on this first slide is actually Bristol. This is the famous Clifton suspension bridge, which was designed in the 1800s. And we're very famous for having a big hot air balloon festival. So these hot air balloons floating over Bristol. It's not quite that sunny here today. We're actually very misty here today, but you're very welcome to come and visit us in Bristol anytime. The little picture at the bottom is actually the building where we normally work, the Merchant Ventures building. I'm at home today, but that's in the centre of town. So Gail mentioned I'm head of the High Performance Computing Research Group in Bristol. We have a number of things that we do, but the thing in particular I'm going to talk about today is this simulator we've been working on for a while called the Simulation Engine, or SimEng. And I've got pictures of the group of developers, which is a subset of our research group, up on the screen here. So the work I'm going to talk about today is mostly done by Jack, Finn, Rahat, and Dan. So, and some of them are actually joining us on this talk as well. So they'll be around for answering some questions at the end. Georg also mentioned some of my background. So I did indeed start off at INMOS. In fact, the very first parallel program I ever wrote, I think, was 1989, and it was in Occam on a transputer. And I was at university in Cardiff in the UK, and I thought this was fascinating. And then when I graduated, I was looking around to what I wanted to do, and an opportunity came up to come and work for INMOS as a microprocessor architect here in Bristol. And I was lucky enough to get that job. And I've been in Bristol ever since. I've been in Bristol for a long time now. And my first job at INMOS was designing SIMD instruction sets. And we were working on, at the time, it was a dual core 64-bit superscalar out-of-order processor, which in the early 90s, this was unheard of. This was really high-end stuff. Today, that's very, very normal, very mainstream. But nearly 30 years ago, this was absolutely cutting-edge stuff. But the most impressive thing about what this team was doing, and you'll understand why this is relevant to the talk later on, is the team had put this amazing, very sophisticated workflow together where there was a structured specification for the instruction set, and it was using something. This was before XML or YAML or any of these things, but it was a sort of structured text file format. You specified the instruction set in this one file, and anything you changed in there automatically rippled out across the entire workflow for the whole processor design. So even the documentation, so all of the instruction set manuals, all built off of this file. The simulators, there were two different simulators. There was a cycle accurate one, and then also just an instruction set one that was faster. The compilers and assemblers all use exactly the same inputs, and all the tests and verification flow were all built off this one file. This had lots of really cool advantages. It meant that you could do design space exploration. We could try experiments. We could ask what-if questions. What if we have more inter-units? What if we change the size of the reservation stations? What does that do? And you just change one file, and everything would rebuild, the simulators, the compilers, everything, and then you could run the experiments. So this was great for actually designing these processors. And I worked at INMOS for a while, and then Gail mentioned ClearSpeed was my last company. I worked for a graphics company called Pixel Fusion in between. And then when I came back into academia in 2009, I had all sorts of experiments I wanted to try in computer architecture, and I thought things must have moved on, must have improved a lot since then. There'll be all sorts of amazing simulators I can use to try these experiments. Now I'm an academic. And it turned out that wasn't quite as promising as I'd hoped. Now, the reason why I want to do this is I'm involved in a project called Asimov. And Asimov is a 5-year project with Rolls-Royce. And this is not the Rolls-Royce car company, unfortunately. It's the Rolls-Royce jet engine company. And Rolls-Royce want to get to the point where they can design new jet engines completely in simulations. They call that in silico. And this is a really challenging high-performance computing problem. And today, it's actually still far from being possible. There are lots of different kinds of physics that we need to model, not just the kind of obvious ones of computational fluid dynamics and combustion, but lots of less obvious ones, electromagnetics, when these jet engines are spinning so fast, they actually become gigantic turbines, electricity generators. And the electromagnetic fields affect the way the engine itself works. So you have to be able to model the electromagnetic effects that are being generated by the engine. Contact and friction has a big effect on what's happening. So this, and also all the thermomechanicals. Many parts of the engine are actually running at temperatures hot enough to melt the engine itself, but the engine doesn't melt, which is lots of clever design tricks are used to make this possible. So these are some of the most complicated objects humankind has ever designed and built. And we want to be able to model them at enough accuracy that you would be confident as you're making design changes. The simulation results were showing you reality with enough confidence. The ultimate goal is to have enough confidence that you could even certify the virtual design. So you would never, you wouldn't actually build the engine until you were happy the whole thing was correct and did what you wanted and was certified, and then you'd actually start making the engine. And we're kind of still a long way off from that, but a long way off might be 10 years. So we're not talking about decades and decades. It's actually a lot closer now than it was. It's becoming possible. We have lots of big challenges. This project actually was one of the finalists for this year's visualization competition at Supercomputing, and it won. So you can now go and see the video. There's a 6-minute video if you follow the link. And Georg, I'll send you my slides afterwards so you can share this with everyone. Follow the link or go to the SE website, go find the visualization section. There are 5 or 6 entries, and there was one from Asimov with Rolls-Royce, and you can go and watch what's going on and see some of the latest simulations. They've got billions and billions of cells, grid points in these models. So we want to help make this possible. And to do that, what my part of the project is looking at is what would be the ideal processor to run these Asimov codes on in the future. So what will really make these codes fly? How much memory bandwidth do we need? How many flops do we need? How big memory hierarchy and what kind of caches do we need? Do we need to do anything clever with cache prefetching or with branch prediction? So we want to design optimal processors to make these Asimov goals and ambitions feasible in the 5 to 10 year timeframe. That's meant we've needed a very fine-grained, accurate processor simulator down at the cycle level. So within cores, we want to be able to model the out-of-order parameters. How wide is the processor? How many instructions can it fetch and issue and execute every cycle? How many instructions can be in flight at any one time? Some of the latest processors, for example, Apple's M1 processors, I'm actually using one in my Apple laptop right now. They can have over 600 instructions in flight at any one time in one core, which is just amazing. These are phenomenal numbers. But what's a good number? Is that too many? Is there still benefit in making those numbers even bigger? How many vector units are useful and how wide should they be? Do we need to do something cleverer or different with cache prefetching? So there's all sorts of questions that we've got that we want to be able to ask, and we needed an accurate, fast simulator to enable that. That's all just inside the core. But then when you go outside of a core, what else is going on? Do we have co-processors on a CPU? Would that help? So these might be co-processors for doing matrix arithmetic. And Intel and ARM have come out with these recently. AMX in the x86 instruction set. SME on the ARM instruction set. These are a bit like the tensor cores that NVIDIA's been adding to their GPUs for some time. So we want to be able to explore those. What about the memory hierarchy? A64FX from Fujitsu just had 2 levels of cache and then high bandwidth memory. That was quite different. Most other processors have 2 levels of local cache and then an L3 shared cache and then another memory after that. So what's an optimal design? How big should these be? I know you had a talk from Jens at Recon a few talks ago, and he was talking about the Lark processor. I'll actually come back to Lark a little bit later on, and that's looking at having much bigger caches to see if that makes a big difference. That's something we'd like to be able to explore, possibly even out as far as the network. So what happens when you go beyond the processor and actually start looking at the network? What kind of network characteristics will we need to support these Asimov types of problems we want to solve. So that's what we want to be able to do. How can we start to do this? How can we actually start to try and answer some of these questions? Well, it turns out we need a fast simulator, a fast process simulator. It needs to be easy to modify because we need to be able to make all these changes and see what happens. It needs to be accurate enough so that when we see something happen, we've got some confidence that relates to reality. And ultimately, this is to enable design space exploration. And ideally, what we call semi-automated design space exploration. So could we use machine learning techniques to actually try a whole bunch of interesting problems and do some sort of search through a big design space, firing off lots of simulations in parallel and see which ones can converge on the most promising configurations of a processor. Now, in theory, we could do this with existing simulators. So Gen 5 is the one you may have heard of. That's very widely used. There are others out there as well. And we actually started off with these, and we did try many of them. And unfortunately, we found for all of them that they all fell down usually in at least one really important way. So either they were just not fast enough, and Gen 5 is actually quite slow, or they couldn't be accurate. We couldn't make them accurate enough, or they just weren't easy to change. So you could maybe do one configuration, but if you wanted to try this kind of search, it just wasn't possible. So in the end, and knowing that I'd kind of done this previously in industry, so I knew this was possible, I came up with the idea of this simulation engine, SimEng, and that's where this came from. And we decided to use similar techniques to LLVM, where we wanted to make the software nice and simple and modular and easy to people to understand and easy for people to contribute to. So we're using that sort of LLVM methodology and mentality for how we're putting SimEng together. So we got some design goals for SimEng. The first one was a primary goal is to make it fast. And we want it to run at millions of out-of-order instructions per second. And that's when running a simulation on just one hardware core. So that's a lot faster than most cycle level simulators out there now. We want it to be really accurate. So within 10% of real hardware. In fact, in many cases, we're much more accurate than that, or within 5%. But usually within 10% is kind of useful. We want the code to be really easy to modify. So that's where our LLVM inspiration comes from. We want it to take you just hours to make quite big changes. You can actually add new instructions in just minutes. You can make quite big changes in hours. In days, you can make a completely different kind of processor. For most simulators, these things would take much, much longer. So it's usually days to add new instructions in Gen 5. And anything radically different, it's months of effort. So this is much easier to use and get started with and to try out. So those are our primary goals. Secondary goals is we don't want to reinvent wheels where we don't need to. So we use several existing frameworks. There's an engine called Capstone, which we use for instruction decoding, and they have support for ARM. And our primary interest is in ARM, but we're also interested in things like RISC-V. So they also support RISC-V, they support x86, Power, MIPS, you name it. It's in Capstone. We're also using the Structured Simulation Toolkit, or SST, which is something that US National Labs have been developing for a long time. And that has some really good models for memory hierarchies. So things like all the different levels of cache, DRAMs, high bandwidth memory, models of all of those are in SST. So we're using that to provide our memory hierarchy models. We're also going to use SST to support multi-core simulations. And we're just starting to work on that now. And then also, where possible, we try and do things compatible with existing simulators. So for example, I said Gen 5 is very widely used. So we try and do, where we do things like instruction tracing, we do that in the same style as Gen 5. We can do Gen 5 style checkpointing, those sorts of things. So we're trying to add value where we really do something that's much better than existing frameworks, and where other approaches already do what we need, we'll just reuse that. So when we first got SimEng going several years ago, we initially started the Marvell ThunderX2. So this was one of the first ARM server processors that was really performance competitive. And this is a microarchitecture diagram of ThunderX2. And this is the level of detail we were modeling it at in SimEng. So we modeled a branch predictor. We would do fetch, decode, and rename. We could fetch 8 instructions per cycle. We could decode and rename 4 micro-ops per cycle. There was a unified reservation station, lots of different execution units, floating point units, integer units. And we modeled the caches as well. We got this working, and we actually got it. The model was very accurate. It was within 5 to 10% of the hardware, and all of our other design goals we were meeting as well. So we thought this is very promising. It looks like we can do this. We can have a fast, accurate, easy to use simulator. So from this, we then stepped back and we abstracted up to a more generic idea of an out-of-order processor. So this is, if you like, the model that underpins what SimEng is actually simulating. So it has fetch, decode, and rename stages. There's an optional branch predictor of any sort. So we have fairly high-end sort of textbook branch predictors, but you can easily change that, plug in different things. There's a reorder buffer. All of these things are completely configurable, so how wide they are, etc., how big the reorder buffers are. Reservation stations can be one big unified reservation station, or they can be split, one per execution unit, or they can be grouped. This is a level of detail that Gem 5 doesn't go into, actually, but we support all of that. A whole load of execution units, as many as you want, as many different types as you want. A fairly clever load store model with a load store queue, and so on. So this is, if you like, is a fairly good abstract model of pretty much any out-of-order processor. We do actually also have 2 simpler models built into SimEng. There's an in-order scalar processor, so you can have a one way just in order. If you want to model one of those, you can have that. Runs a bit faster. And we have a sort of an atomic model, which is really just an instruction set simulator, and that runs faster again, but doesn't have really any accurate notion of cycles. So this is our abstract model, and we can use that to model almost any kind of processor that exists today, and even, and this is the interesting bit, hypothetical processors of the future. And this is what we really want to get into. The way you configure one of these models and actually make it a real model of say, an actual processor is we have YAML files, and you actually just tend to have one file, one configuration file for one processor. I've just picked out a couple of examples here. So in a YAML file, you can set, are we out of order or in order? You can pick a clock frequency, how fast the timers run, how wide, how many bytes you fetch at once for instructions, whether you use micro-ops or not, how wide the vectors are in bits. And then here's some other examples about the load store queue, the interface to the L1 cache. What's the access latency? Is it exclusive or inclusive cache? How wide the load store bandwidth is? How many outstanding loads you can have on each cycle? All sorts of things like that. And there are lots and lots of these options that you can all configure. And it's very easy for you to add more. So that's the other thing. If there's something that the simulator doesn't include, actually modifying it and adding something that you want is very, very straightforward by design. Here's some of the other models that we are supporting now. So after ThunderX2, we modeled the Fujitsu A64FX. That was very important to us. We had this model actually before A64FX appeared in the real world. So we were going from the documentation. We had a pretty good model. Then once Fugaku became available, which was the #1 supercomputer for a long time, we actually could use the hardware to refine this model and make it even more accurate. So I have a very accurate model of Fujitsu A64FX. And then more recently, we've added ARM Neoverse V1. So this is the kind of core that's inside the Amazon Graviton processors. Again, this is a very, very fast, very wide, powerful processor. And most recently, we've added a model for the Apple M1 core. And this is the highest performance, most challenging core we've modeled so far. It's got something like 14 different execution units. It can have over 600 instructions in flight at any one time. It has a huge reorder buffer. This one's a really complicated one, but the same SimEng with just different YAML files is modeling all those different designs, and it's very straightforward to do. and it's fast for all of them as well. So where we got to in terms of our current work and some work in progress, we're mostly focused on ARM, and we're up to fairly recent ARM instruction sets, ARM v9, with support for their latest vector instruction sets. So that's SVE and SV2. And also their new matrix instruction set, SME, a Scalable Matrix Extension. I'll come back to that and say a bit more about that in a few minutes. We're supporting nearly 1,000 instructions, which is about 15% of the entire ARM instruction set, or at least the instruction set as supported by Capstone. Now, you might think that's not very many, but essentially this is all of the instructions the compilers actually generate. We've run lots and lots of different programs, and occasionally we'll find a program that we use an instruction we haven't implemented yet. We can add that in. Usually it's a few minutes, might be a few hours if it's something a bit different. So this is kind of all of the instructions that you need to run real programs. We've added the Scalable Vector Extension support, the vector instruction set support, to match the Fujitsu A64FX and Graviton 3 and other ARM cores as they come out. And in that, you can play with the width of your vectors and how many vector units you've got. So you can try experiments. You can ask, well, does A64FX have the optimum length vectors or not? What happens if you make them wider or narrower, or you have more of them? We can actually try those experiments with the simulator now. That's all with ARM. We have added RISC-V support, and Dan Weaver, whose picture I showed at the beginning, he's been working on RISC-V. So we have some initial support for RISC-V as well, with various sets of the RISC-V instruction set. More of that's coming, this floating point going in soon as well. We could support things like x86. Capstone already has that. We don't have any plans to do that ourselves at the moment, but most of the things we want to do, we can do with ARM and RISC-V. We do things like syscall emulation. This is so that you can run real runtimes and run real binaries. So the binaries we're running to the simulator are real binaries just built with standard compilers. And we now have full integration with the, I mentioned SST earlier on, and we use that for the memory hierarchy. So if you don't want to use SST, you can just pretend you've got an infinitely sized L1 cache. For lots of things, that's good enough. But now we've got SST integration that seems to work really well. Things that we've run through the simulator, we've tried lots of different C, C++, and Fortran codes, primarily from the high performance computing space. This is what we're interested in. You can build your binaries with lots of different flavors of GNU. We've used the ARM compiler, ARM Clang, including the most recent ones. There are some current limitations to be aware of if you want to give the simulator a try yourself. The binaries you run, they really need to be statically compiled. So that means not using dynamic binaries. So all of the code is statically linked into one monolithic binary. We are looking at how to support dynamically linked binaries. It turns out trying to run MPI programs is really hard if they have to be statically linked. Not impossible, but it's almost impossible. So we are trying to figure out how to support dynamically linked binaries. It's much more complicated than it sounds in simulation. So we've been looking at this for a while. We've got a couple of different options we're investigating. But if you can statically link a binary, that's easy. We can run OpenMP codes. We've got single rank MPI. At the moment, we've only run single core simulations. So we have been able to get a single rank MPI working. We're trying to find a more general way of making that work. There's some special cases where if you've got objects in memory that aren't from the binary, there's this thing called the VDSO, Virtual Dynamic Shared Objects. We don't officially support that yet. But pretty much most, if you take an HPC benchmark and you can make it run on a single core and you can turn off MPI, you should be able to compile that and run that binary to the simulation, and it should work. And we've run things like MiniBuild, which is a quite widely used compute-bound benchmark. We can run Stream and Babel Stream, things like that, and model the performance going through the cache hierarchies. We can run Cloverleaf and Tealeaf. These are two codes that are now in spec HPC. So if you look at the latest version of the spec benchmarks, we've run those to the simulator. We can run FFTW, including building the plans and all that sort of stuff. So we can run pretty complicated things through the simulator and get interesting numbers out of it. And we can even, going right back to the simulators I used to work on in the 90s at Inmos and following companies, we did a little retro thing for SimEng, where we've got effectively a text-based instruction trace tool. So this is harking back to terminal-based interaction with simulations, if you like. But it takes the instruction trace from the simulator. So in this main window, this is a trace from the simulator. I think it might be running stream. I'm not quite sure what it's running. I can't remember. On the left, we're then showing where these instructions are in a pipeline. And this was a ThunderX2 model, so it could fetch and decode and execute 4 instructions per cycle. And you can see we've got F is the fetch stage, D is decode, N is rename. Then we've got dispatch, issue, I is issue, C is complete, and R is retire. And you can then follow the progress of instruction batches as they're going through the pipeline in this 1990s style instruction tracer. We'll eventually we'll get around to putting a proper GUI on this at some point, but it's quite useful already. And then at the bottom, it tracks all sorts of events as they're happening, like we're getting stalled because the load store queue wasn't ready, or there's a branch mispredict or something like that, and those things get highlighted at the bottom. So this is quite useful for tracing through the simulator output and seeing what's happened and why things have been stalling, not just how many cycles did something take to execute, what's actually causing these stalls, and actually getting right down into the detail of what's going on. So that's the trace viewer. So what are we actually using this simulator for? What kinds of experiments are we actually doing with it? And that's the really exciting part. Now we have this capability. Well, I mentioned Lark and your recent talk by Jens from Recon. And one of the things we've just done in the last few weeks is some work with Recon, where we now have a model of Lark using SimEng. So the first Lark model actually used Gen 5. The problem they've got is it's very, very slow, and it's not very accurate, and it's very, very difficult to change. So it takes a long time to try a different configuration, to try different experiments. So what we've done is we first started out with, on the left, we're running streams through the A64FX hardware, because Lark is closely based on A64FX. Then the middle column is our A64FX simulation. So this is the SimEng model of A64FX, and we're within 5% of the hardware for stream. And then we took our A64FX model and we tweaked it using the parameters of the Lark processor from the Lark paper. And then we can run the same experiment through Lark, but it's running 4 to 5 times faster than the previous Lark model. So Recon are very interested in this, and we're hoping that we can get them set up to use this model, and they'll be able to do many more experiments and try more interesting things. On the right-hand side, this is running a cache bandwidth benchmark. So this is benchmarking all the different levels of the memory hierarchy, see what bandwidth it's got, using the A64FX hardware and the SimEng model of A64FX, and then the SimEng model of Lark, and actually modeling the different performance there. So we have a Lark model in SimEng already. So that's something we're hoping we'll do a lot with Recon next year. Watch this space. Other things we've been doing, I've mentioned exploring vector designs. So how many vector units should you have? How wide should they be? When you ask processor designers how they've settled on, for example, A64FX was 2 times 512, 2 vector units, 512 bits wide each. Different Intel processors might have AVX 512, but how many units do they have? AMD processors were having 256-bit wide vectors, but having more of them. Different ARM cores are looking at having 128-bit wide vectors, but lots of them, maybe 4, possibly more than that. What's a good width? What are the different trade-offs? And there hadn't been much rigor going into those experiments, and that's something we really wanted to be able to start looking into properly, in a properly scientific way, with a proper methodology, properly rigorous, be able to really test assumptions and see what happened. So this is actually work that Jack Jones has been doing, looking into varying vector widths and seeing what impact that has. And he tried something very interesting. He built a hypothetical model of a processor that has an unfeasibly wide front end. So this is a processor that can actually execute 64, or it can fetch and decode and issue 64 instructions every cycle. Well, that's much, much wider than any real processor. But it doesn't matter for this experiment, because what he was trying to ensure was that the front end wasn't going to be the bottleneck. He's really interested in what happens at the back end, i.e. where the execution units are. And he really wants to model what happens when I add more and more vector units, what happens if the vector units get wider and wider. And he didn't want the front end to interfere with that in any way. So if you like, he's got it's for all intents and purposes, infinitely wide front end. So as many instructions being fetched and decoded and issued every cycle as you need. And then the back end, where the execution units actually live, that's where we're going to try these very rigorous experiments. We're going to vary the number of vector units, and we're going to vary how wide those vector units are. And Jack tried 2 experiments. What happens if you have one vector unit, but it gets wider and wider? It starts off at 128 bits, and then goes 256. And actually in SVE, you can go up in multiples of 128. So not just powers of 2. Probably the interesting widths are powers of 2. So you can do 128, 256, 512, 1024, all the way up to 2048-bit wide vectors. No one's done that recently on a real processor. Up to 512 bits is the widest on recent hardware. But we can try all of that in simulation. And then the other experiment was, what if you have a fixed width in total? So your total vector width is, say, 2048, and then you chop that up into different pieces. So you might have 1 times 2048 bits, or you might have 2 times 1024, or 5 times 512, sorry, 4 times 512, and so on. And then try those, say, well, does one of those have any advantages over any of the others? And see what happens. So those are some experiments that Jack set up. Then he looked at some common kernels from linear algebra, so from BLAS. So DAXB is one of the L1 BLAS routines, and here's the core loop from DAXB. Turns out that was going to take 3 cycles, and what we have is simulated results as we increase the vector width. So this is one vector getting wider and wider. So 128 bits, 256, 512, actually simulating that. And then also if you plug in, it takes 3 cycles to do the main loop. And it's for about 500,000 elements, so very long vectors. What happens? Just plugging that into a theoretical model, how many cycles do you think it would take? That's what the line's representing. You see the simulation of this processor was actually bang on what we were expecting, how many cycles it was taking. And essentially, as the vectors get wider, it was almost perfect speed up for this really, really simple case. That's kind of no surprise. If you like, this is a simple case that does represent something real where we know what to expect. So it's quite a good test to see if the model was performing as expected. And essentially this says the model is doing what we thought. So then you can try more complicated things. So now you can take dgem. This is actually taking real dgem code from the ARM performance math library. So not code that we made up ourselves, so not a naive code. So this is doing multiplying 2 matrices A times B, adding them to a third matrix C. There are some scalars that get multiplied into some of these matrices as well. So it's a little bit more complicated. But we could do the same thing where we can actually simulate this as we let the vectors get wider and wider and plug the numbers into a hypothetical model. And they almost actually not perfectly exactly coincide, but they're very, very close within a few percent. So again, we can be confident the model's doing the right thing. And then we can start looking at a bit more detail of what's actually going on as we're increasing the width of the vectors. And what we're showing on the right-hand side is the vertical axis is how many cycles it was taking to run this problem. By the way, the matrix size was an M of 256, N was 128, and K was 256. If you're doing matrix multiplies, you'll know what that means. And then on the x-axis, we're showing what the vector configuration was for this simulation. So, for example, on the left column, we've got 16 vector units, and they're 128 bits wide each. Then we've got 8 units of 256 bits each, 4 of 512, 2 of 1024 bits, or 1 just one vector unit that's 2048 bits wide. And you can see the total cycle count is roughly the same. It does vary a little bit. The fastest one was actually 4 times 512 bits was the fastest, was actually faster than 1 times 2048, and faster than 16 or even 8 by 256. So the fastest was 4 by 512. And we can look at other interesting things as well, like where in all of these, where are the stalls occurring inside the processor? And we're most interested in the back end because that's where we're really changing things. And we can see as we make, for example, as the vectors get wider and wider, we start to see more back end stalls. And that's, I guess, because we're waiting. You have to wait for a longer period of time before you have a full vector that's wider and wider to actually start executing. So the sweet spot in this case happened to be more shorter vectors rather than fewer wider vectors. And there's all sorts of different experiments you can try with this. I'm just showing a few highlights. Ultimately, what we can do with this is we can take real models. So here's another example, the ARM V1 core. And this is on the left, we've got the sort of top level microarchitecture of the real V1 core. Lots of different execution units, including SVE. They actually have 2 256-bit vectors in the V1 model. And then we can say, well, what if you take the V1, but instead of having 2 256-bit units, we have 1 512-bit wide unit, or even 4 128-bit units? What happens? And again, we can run things like BLAS. So we have DAXB and DGEM. We can run those models with different vector widths, different numbers of vector units, and see what happens. And it turns out that actually if V1 had 1 512-bit wide unit, it would actually be faster for L1 BLAS and L3 BLAS, at least for BLAS, right? Whether this makes much difference to other codes, that's a different question. But for BLAS, wider vectors would actually have helped for V1. So we can try all sorts of hypothetical questions and take some real cores and play around with those. We can do the same with A64FX. What happens if its vector units were wider or narrower, and see what happens. So this is some really interesting things that we can do now. We're also looking at ARM's Scalable matrix extension. So this is implementing the new matrix unit. We've currently got 7 most important instructions supported for that, modeling that as an in-core accelerator. By that, I mean, this is an A64FX model. So again, this is actually A64FX, but then and it's Finn Wilkinson who's doing this work. What we've done is we've added an SME unit as if it were extra execution units inside the pipeline. There are different ways of doing it. You can actually add SME effectively outside of the core, and then you keep feeding instructions from the core. But we've tried it this way initially to see what happens. So this is basically A64FX with and without SME, see what happens. And then again, we can try all sorts of experiments. So this is some work that Finn presented at the PMBS workshop at Supercomputing in Dallas 2 weeks ago. Now, time's going quickly. It was like last week. And we can look at basically the first columns are A64FX without SME. And then we got 2 different versions of SME, and the 2 different versions of how much work they can do in parallel. This was doing a one matrix multiply size, and you can see as the input size gets bigger and bigger, up to 256 on the side, you get more and more speed up to 6x speed up using this hypothetical SME core instead of just using SVE. So that's quite interesting. And then you can look at things like for Resnet. So this is one of the AI kernels, which spends most of its time inside gems, so matrix multiplies. We can look at the A64FX hardware, then our A64FX simulator, and then our A64FX simulator with SME. How much does that save you on instructions? So 3 times fewer instructions for this small gem case. What it does on cycles, so it saves you lots of instructions, but only 20% of the cycles. What it does to gigaflops. And we can do the same for a much bigger gem as well. So a big matrix multiply. Actually, it saves you a lot more. It saves you lots more instructions, about 9 times 3 instructions, and a bigger speed up. So that's an 80% speed up on cycles, but still not, it's not 9 times, right? So 80%, maybe that's really worth it. Maybe you're expecting something more than that. So lots of different experiments, and we're really just getting started now with what we can do there. What's coming next? Well, we've got lots of things we're planning on doing with the simulator. We've got more core models coming. Our M1 model is very new, so that will be refined. We're planning on doing an NVIDIA Grace core model, which is an ARM near Versa V2. That's quite quick and easy for us to do. And once we've got hardware, we'll be able to make that quite accurate. We're planning on adding multi-core support. That's with SST. The memory hierarchy is actually now in good shape, so that's already pretty good. We do want to keep running different codes through the simulator so that we can make sure we've got all the instructions there we need to support. We're trying to get, we'll eventually try and get all of spec CPU working, for example. We've mostly focused on the ARM compiler and GNU. We have had a little bit of Cray working before, but we'd like to be able to build binaries with NVIDIA and Cray. Usually this means a few instructions will get generated we've not supported yet, possibly some system calls we need to add as well. All of that's fairly easy for us to do, just needs a bit of time. Planning on looking at some advanced branch prediction that we want to add and cache prefetching. The RISC-V support is new. That is in the latest release, but we're adding floating point support. That's still to come. We want to test this running on lots of different operating systems. We've tried quite a few, but we want to make that much more robust. And there's all sorts of tooling. We want to make it easy for people to do this automatic design space exploration, including us, because this is what we want to spend our time doing. So just a few conclusions now. So SimEng, it's now letting us do some really nice exploration in microarchitecture and some nice new research. We can now easily make changes to a microarchitecture and try all sorts of interesting ideas that we've got about this future processor we'd like for running Asimov codes on. We're about 4 to 5 times faster than Gen 5, and we're more accurate at the same time, while we're much easier to use and much, much easier to modify. So those are our main design goals. We're using SST for a memory hierarchy, and that's working well. We're going to try and get multi-core working over the next couple of months. We're going to try and get multi-core running in parallel, so model 1 core per real hardware core, and see how we can get that going. So we basically now have a really fast, accurate single core model. The actual base software for the out of order model is about 10,000 lines of C++, that order, might be 12,000 lines, a fairly straightforward C++. So what else can you use that for? Have a think, and you can give this a try. I've kept the link for the GitHub repo for the group, and the SimEng repo is very easy to find in that. If you Google search for SimEng, you should be able to find it quite easily. And then just one last slide. We're funded by the Asimov project and also by an ARM Centre of Excellence in Bristol. And the SimEng project was actually started by one of my original students, Hal Jones, and then he was supported by James Price and Andre. And then lots of other people have contributed over the years as well. So with that, I will finish, and I will hand back to Georg and for hopefully some questions.
Thanks a lot, Simon, for this very interesting talk. There are questions, I guess. Philip Susanek, please.
I would be really interested to learn a little bit more what's behind. What did you do to make it so fast? What's different to other simulators? And how do you make it so flexible and configurable? Is that lots of template magic in C++, or what's behind all this?
That's a great question. It's actually, that's one of the most regular questions we get asked. It's like, what's the magic? And it's interesting. Basically, there is no magic. The main thing is we set performance and simplicity and ease of use as primary design goals. And then as we've been developing the software, we're constantly testing against those principles. So we're looking at, let's say we want to add a new feature. We'll look at it and say, okay, how accurate do we need this to be? What's accurate enough? Is it going to really slow down the simulation? If it's going to slow it down a little bit, that's okay. If it's going to slow it down a lot, it's not okay. And we have this rigorous set of principles that we are strictly applying as we're constantly developing the code. And when people submit pull requests, they're all reviewed against those principles. And we're often sending things back and saying, sorry, we can't accept that because it's made the code too complicated, or we can't accept that because it's slowing it down too much. Please fix that, speed it up, simplify it, find a way of doing this in a better way, and then come back and then we'll accept it. And it's having those design principles and actually accepting or rejecting contributions based on whether they meet those goals. That's what's doing it. We're also doing regular code reviews, and we're doing regular reviews of where the bottlenecks are in the simulator and how we can make it faster. And that's it. So there's no clever magic tricks. There's no particular set of techniques. It's a real care and attention to simplicity, to sticking to the principles, to sticking to the rules. And that is quite tough because it takes more effort in reviewing pull requests. It takes more discussion with contributors to make sure they understand what we're trying to do and how we're doing it. But the payback is worth it. And we do say this is very, very similar to the LLVM methodology, where LLVM and GNU, if you look at them, there's no magic in LLVM compared to GNU, but LLVM is much, much easier for people to get involved with as a project, to contribute to understand how the code works, to add new features compared to GNU. And the main differences are the way it's developed. And it's those sets of rules, and LLVM are very strict about what gets upstreamed and how they accept things into the code base, and they maintain that discipline and that rigor and those design goals, and everyone has to stick to them. And that means that LLVM without that would degenerate back into something like GNU. That sounds really harsh on GNU. I didn't mean it like that. What I meant was it would become harder to add new features, and it wouldn't be as simple to get involved with and things like that. So most of this really is about methodology more than technical tricks. But we do constantly do lots of profiling and testing and reviewing.
Yeah. And the configurability, is that templates that you use to make that work,
there is some templating.
To what degree, how low do you go in terms of simulating the hardware? So this is more a high-level interface in terms of the functional units that are in there, not right. You probably don't go very much deeper than it's necessary.
No, that's right. So we don't have to model the bitwise how you do a floating point operation. We can just use a floating point operation from the host, right? But we are modeling that a floating point unit has a reservation station, and how big is that, and all those. So we do go down to quite low level of detail. But once you get to sort of the fundamental operations, integer operations, floating point, that just becomes a floating point add or an integer multiply on the host. Yeah. The code is simple enough that I would encourage you to actually just go take a look at the website, go take a look at the code, and just have a peek inside it. Look at the branch predictor and see how it works.
Interesting. Very interesting.
How do you model, for example, the memory traffic? Because we have seen, for example, when you compare different architecture, for example, within the caches, some data traffics can overlap, some cannot overlap, and stuff like that. So how do you model this?
Yeah, no, great question. So in some ways, the way the memory hierarchy works and the way that the microarchitecture, the core model, interacts with memory is probably the most important thing for actually accurately understanding what's going on. And we've taken a few years to get this to where we want it to be. We started out with very, very simple models of how it all worked. And a lot of the interaction is really between the load store units and the memory hierarchy. So we started out with fairly simple models, and then over time we've refined those as we've understood how the hardware works. And so even with ThunderX2, the load store queues were actually quite complicated, and they could have lots of different outstanding loads and stores, and whether they could do how many outstanding misses you could have, could you do a hit under a miss? So could a load which hit the cache overtake a load which had missed the cache, and all these sorts of things. So we can now model all of that, and most of that's captured inside our load store units. and they've had a lot of work. Our load store models had a lot of work on it over the years. And each time we had support for a new core, so when we went from ThunderX2 to A64FX and now to V1, we're always looking at that, see what new things they support that we haven't had before. But we've seen most things now that load store units can do in supporting a complicated memory hierarchy. And now with SST, we can support quite complicated memory hierarchies as well, where you've got all the different caches all doing different things at the same time. It's quite interesting with I mentioned SME, so the Scalable Matrix Extension, actually where a coprocessor like that goes to get its data from, it doesn't really make sense for it to stream its data through L1, for example, because that tends to just completely pollute and destroy everything in L1 that everyone else was using, when it's normally just streamed. So there's no temporal locality to data that you want to go through to a matrix coprocessor. So often something like SME, you might want to connect directly to, say, L2 cache rather than L1. And you can actually play around with where SME would connect to. Is it going through L1 or L2 or even L3 or even straight to DRAM and not using any of the caches? You can try all that in simulation and see what happens. But yeah, so these things are very complicated. They're almost like little out of order engines themselves, modern load store units, and we've got pretty good models of that in SimEng now. So
do you do manual work to find out this, how this works, or the model works, or is it some automated or something?
Right.
Right.
Yeah, no, good question. A combination of things, probably at least three different things, actually. So one is we tend to start with documentation where it exists. The A64FX actually has some of the best, most detailed documentation of exactly how the microarchitecture works and how many cycles everything takes that we've seen in a long time. Most of the time, you don't get that. So then with, say, ThunderX2, as well as having documentation, we talk to the implementers and we'll try and learn as much as we can from them. And then the other thing we do a lot of is actually try it out. So actually try hardware once the hardware becomes available. And then we're trying little synthetic code sequences or microkernels or all sorts of things. And lots of other people do this too. And we'll often take what other people have done and how they've understood something works, and we'll plug that into our model. So, and we're using those three different things to sort of refine each other to find which was the most accurate and where there's some details that, say, the documentation had left out or we can't get from the hardware. Yeah. So yeah, it's often lots of kind of Agatha Christie style detective work to try and figure out exactly how these things are really working.
Thank you. Yeah.
Some would call that reverse engineering, but the companies don't like that term.
Yeah. My magnifying glass, Hercule Poirot style.
Yeah.
There's stuff which is sort of generic across all architectures. For example, how large is the reorder buffer, or how many ports are there, and which units are behind which ports and such things. And I can see how it is easy to put that into a YAML file to make it configurable. But there are other things which are really specific. For example, in the A64FX, the presence of these two reservation stations, or another CPU, something that's really specific to the CPU, and that's probably not as easy to generically describe in a YAML file. So how do you handle this?
No, that's absolutely right. So we think about this a lot. And actually what you end up doing sometimes for some models is something would end up going into the code rather than into a YAML file. So you would end up with a model specific version of, I don't know, that let's say the file that deals with reservation stations. So it might be something like that. Another example might be which execution units can bypass or operand forward to others, and we've got some generic versions of that. So where you can either say all units can bypass to all execution units, or none can, or there's a specific set. And we did that because being able to forward everything to everywhere is quite common, but then A64FX has this quite specific set of what can forward to where. So that's something you might be able to capture some of that in a YAML file, but then other parts of it might be just too complicated. And then you specialize, say, the source code for that model. We try to avoid that as much as possible, because that's when you start to get the proliferation of lots of different versions, and then it's easy to forget one and it breaks when you're changing other versions of the files. but sometimes you can't avoid it. So that is possible, and we don't stop you from doing that. We don't, and we don't stop ourselves from doing that when that's the best way of doing it. But most of the time, if you can capture it into a generic YAML type configuration, we do that. But you can specialize the code.
Okay, thanks. Another question about your DAXP results. So what you observed is in the first experiment that performance scales quite nicely with the vector width. Yes, this one. Yeah. So that can only happen if the data delay through the cache hierarchy is negligible. But you have 500K elements. So am I right in assuming that you assume an infinitely large L1 cache here, or what? How is the data delay handled?
That is a great question. Now, I think Jack is actually here. Are you there, Jack? Because if you are, if you're able to unmute, we can hear this. We can hear the answer from the horse's mouth.
Yeah. So in that experiment, unfortunately, that was before we had SST going, so it was an infinite L1 cache interface, and at the time, all we had was a delay in, let's say, reading or load some data from that infinite L1 cache, and then that would be different for, I don't know, whether it's like an integer load or a SV load or a scalar load or something like that. But yeah, at the time it was an infinite L1 cache.
I guess we could redo this now. We've got SST, right?
That's the plan. Yep, that's on those cards on the table.
Cool.
All right, thanks.
I have a question about the usability. How do you use the tool? Do I just throw my binary on it and it puts out all of this numbers, or do I have to prepare special sections and say I want just to have the analysis for the section of the code, or how does it work?
No, great question. So it should be really easy to use. We've worked quite hard to make that true. So actually downloading, installing the simulator should be quite straightforward. If you hit any issues, we'd like to hear about it actually. So if you give it a try, do let us know if you hit any complications. And then you just build a standard ARM binary. And like I say, today, if you use GNU or the ARM compiler, that should be fine. You tell it to build a static binary, and there's a special flag you give it, tell it to do that. And that's all you need. And then you just run that binary through the simulator and off it goes. And then you can tell the simulator what you'd like to know about what happened. So you can tell it what kinds of output you would like to see, what kind of information, what kind of performance counters you would like from the simulation. But it should be as easy as that. And there should be some fairly straightforward kind of instructions on the website for the simulator as well. Actually, what I'll do, maybe if because I haven't got my web browser up at the moment, Jack, if you find the URL for the simulator directly, do you post that into the chat, and then it'll be easy for people to click on and go and check it out. Thanks. Yeah. So if anyone does give it a try and you hit any problems, please let us know, because we normally jump on things and fix things very quickly if you do hit any snags.